Then once we have the bias values, we want to actually take them and we want to come up with the baseline predictor. And so we just basically add the bias values in from that. And so here's a tabulation of the bias values that we just computed, just in table form. The users are over here and the movies are over here. And so we'll start with user D and movie 3. And we'll just illustrate just a few of these computations, just 2 of them. We'll just do, for instance, user D, movie 3. So D and 3. Remember, we start with the baseline, or the raw average value of 3.5. Then we add in the bias of user D, which is negative 1.5. And then we add in the bias of movie 3, which is 0.75. So remember, D is a harsh critic, and 3 is a good, quote-unquote, good movie. And when we do that out, we come up with 2.75, this value. So it's lower than the mean. We expect this to be lower than the mean. And the intuition there is that movie 3 isn't as, quote-unquote, much better than the average. Then D is, quote-unquote, more of a harsh critic than the average. So they don't quite cancel each other out, and we do end up going below the average here for this pair, D3. Let's try user A, movie 2. So we have A2, and that's a value that we don't already know. For D3, we do have that value. Now we want to try A2 for something that we don't know. So we do A2. We get, we start with the mean again of 3.5. Then we add the bias of A, which is 0.83. And then we add the bias of movie 2, which is negative 1.17. So again, this is more negative than this is positive, so we're going to go below the average, and we get 3.16 here. So it's a little more below the average. And if we continue that out, we do the baseline for all the values. This is what we'll get in this table here. Just to note, for instance, some of the values or this only one value actually is 5.00. The reason that it's not, if you did the calculation out for 4, you would have a bias of A 0.83 and movie 3 0.75. It would go above 5, but we clip them at 5 because it's not possible to be greater than 5. So therefore we just clip, and that's a kind of an important point. The reason we clip them at 5 is because we know the rating can't be greater than 5, so we'd only be hurting ourselves by pushing it above 5. So if it goes above 5, then we just hit it at 5, and if it goes below 1, then we just assume that it's 1. So we remember, we can only be between 1 and 5 here. So now once you do this out, then we can do the RMSE. Oh, and just let me say here also, this is a 5, so that's clipped, and this is a 1, that's also clipped. So you can do that out. You can see from D2, for instance, D, that's going to go below because 2 minus 1.5 minus 1.17 is already actually a negative number. It's below 0 even, so we just clip that at 1. So now the RMSE, we'll do the RMSE of the test set. I'm just going to do it. I'm not going to do every step out this time. I'm just going to do it all in one single step. So again, we do the square root, and then we have to find the mean of the squared errors. So now we'll write out these squared errors terms. So we have 4 and 2.80. So this is 4 minus 2.80 squared, plus, now the second one, this is 2 minus 1 squared, plus, in the third one we have 5 minus 5 squared, which is just 0, because 5 minus 5 is 0. The fourth one we have 3 minus 3.5 squared. And then the fifth one, it's kind of running out of room over here, but now the fifth one we have 4 minus 3.85 squared. And we divide that by 5 because we're averaging everything. So I'm going to write out just what each of these terms are when we square them in here. We get, this is 1.44. This is 1 clearly because 2 minus 1 is 1. 1 squared is just 1. We have 0, as we said. We have a 0.25. And we have a 0.0225. That's all divided by 5 to average it, and then we take the square root of the whole thing. And then that, when we do that out, we get 0.7365. That's the RMSE for the test set. If we do the training set, we will get 0.4709. And I won't do that out again because there's 20 of those terms, which would be a lot to write on paper, but that's the idea. So now we can compare this with the RMSE that we had before, and so now we have an improvement. If we do an improvement over that 1.0247, which is what we had before the RMSE, the test set, just when we did the raw averaging, we're down to 0.7365 now. So if we want to find the percent improvement over that, we just do we start at 1 because everything is starts at 100%. So we're trying to find the percent improvement. So basically what we're going to do is we're going to find out what fraction we are of that right now. So 0.7365 is where we are now, and we were at 1.0247, right? And so we do 1 minus that because we're trying to find the percent improvement. So the lower that we are relative to this, the better. And we multiply that by 100%, and we get 28.13%. So we're improved almost 30% over what we had before. And then for this guy, the improvement's actually more like 59%. So you can see that again, we did much better than we did when we just did a simple raw average. And so that's somewhat explaining the utility of using this approach. But know that the percentage improvements are going to be way different depending upon what example. This is only one example. And in fact, the improvement could be negative, in which case we're actually getting worse. So it's not always guaranteed that we're going to be getting better, especially if there's some unknown patterns in the data. But on average, we expect intuitively that incorporating this is going to make our prediction better.